directions that you use. Okay, so we'll do a direction with respect to the z-axis, and so this angle is called theta, and then you will project the vector on the xy plane, and then this angle is called phi. Okay, so the three numbers that you need to specify this vector, the vectors are denoted by a letter with an arrow on top, and this can be specified by a, the length of the vector, theta, and phi. Yep. All right, so here are these quantities. These quantities will be represented by vectors. So here's a vector. It's a new mathematical object. Okay, it's not a scalar. It's more complicated than a scalar. Why is it more complicated than a scalar? You need more numbers to specify it. For a scalar, you need one number to specify it. For this vector in 3 dimensions, you need 3 numbers to specify it. It's 3 times more complicated. All right, so what are we going to do about it? All right, so in mathematics, when you learn about a new quantity, how do you get to know it? Yeah? I'm sorry? Okay, so when you want to get to know people, you talk to them. When you want to get to know a mathematical quantity, what you do is you learn to add it. How do you add it, subtract it, and multiply it? That's what this chapter is about. Okay? We'll learn how to add, subtract, and multiply vectors. Okay? That's what this chapter is. All right. Now let me show you how to add vectors in pictures. And then we'll learn how to add vectors algebraically, because pictures, it's hard to draw pictures accurately. Okay? But adding vectors in pictures, that's a good thing to have in your mind. Okay? So you understand it better. Okay? So again, here's a vector. Okay. A vector, the length represents the magnitude of the vector. So if this was 50 miles an hour, what would 100 miles an hour in that direction be? What would you do? Twice as long. There you go. So you know intuitively. And 50 miles an hour in the opposite direction? Yeah, exactly. All right. So you know what that means. Now here's the deal with vectors. Okay. Let's say you drive 50 miles an hour north on I-95 and 50 miles an hour north on Nova. Are your velocities different? No, they're not. So they're the same. Okay, so that's one thing about vectors. This vector is a vector. 2 vectors are equal as long as their magnitudes and directions are equal. It doesn't matter from where you draw them. Okay? So that's a vector. Now, intuitively, you probably know this. What is 2a? What do you think that means? I'm sorry? I'm sorry? Yeah, double the magnitude. Very good. Okay, so you intuitively knew that. But here's what you've done. See, this is a vector. What is this? A scalar. Without even thinking, you learned how to multiply a scalar to a vector, and you knew what that meant. What is this guy? Yeah, so what you did was you multiplied -1 to this vector, and you knew what that meant. Okay. All right, so now let's do the next step. Okay, so here are 2 vectors. You know that you can move vectors around anywhere you want. Okay, and if somebody asked you what is this fella? Okay. They're asking you to add these two vectors, and here's the rule. Okay. So you take the tail of the second vector and place it on the head of the first vector, and this sum is this guy. That's A plus B. Okay. All right, so that's how you add vectors via pictures. Yeah. Now, this is good to have in your mind, but this is not a useful practical way of adding vectors, and we'll show you a practical way of adding vectors in a second. Okay. But once you know this, let's say I add a third vector C. Can you do that? Sure. All you do is you keep doing that procedure that I showed you. And the sum is from the first vector to the last vector. This is A plus B plus C. All right. So once you learn how to add two vectors, now you can add infinitely many vectors. It's no problem. Okay. All right. So let's do this. So vectors are denoted by directed line segments. Their length represents the magnitude, and their direction is the direction of the vectors. These are two-dimensional vectors in 2 dimensions, so all you need is just 2 numbers to specify them. Their magnitude and direction. Okay. The magnitude of a vector is denoted with just a letter without an arrow. Here's the notation for a vector. This also represents the magnitude of the vector. Okay. So here's the first physical vector, displacement vector. Let's say you go for a walk from point A to B. Okay. Your displacement vector is a vector pointing from your initial point to the final point. That's your displacement vector. See, you could have walked along that path, along this path, along that path, and the displacement vector is the same. Okay, so the displacement vector is just from the initial point to the final point. You could have walked in an infinitely different number of paths, and you'd get the same displacement vector. Okay, here's a vector A. 2A is just twice as long. Minus 2A is twice as long in the opposite direction. Yeah. Like I said, this vector is equal to this vector. For two vectors to be equal, they have to be pointing in the same direction and have the same magnitude. Doesn't matter where you draw them. Okay? This is true on a flat surface in Euclidean space. If you draw vectors on an orange, you draw a vector here and a vector there, that'll be different. Okay? You guys following this? Okay. So here are two vectors. You want to add them. So here's A. We'll keep A right there. We'll move B over there. And C is the sum of A and B. Yeah. Hello? What happened?
I'm going to use the bathroom.
I'm sorry?
Can you use the bathroom?
Here's A. If you're adding several vectors, A, B, C, D, E. You keep adding vectors tail to head, and then the sum is A from the tail of the first one to the head of the last one. Okay? So this way you can add as many vectors as you want. Okay, so what this slide shows you is the following. Okay, again, what we are doing is we're getting to know this new quantity called a vector. Okay, and then what you do is you see if the behavior is the same as how numbers behave. So, for instance, 4 plus 5, is that equal to 5 plus 4?
Yes.
That's true for numbers. So you want to see if that's true for vectors. Okay? So if vector addition is commutative, that's what that means. Okay? So you can, when you add two numbers, you can switch them around and the result is the same. Okay? So we want to see is A plus B equal to B plus A? Is it commutative under addition? Okay? You'll find that it's not commutative under multiplication. For instance, you will see in a little bit, for numbers, 4 times 5 is the same as 5 times 4. For vectors, A cross B will show you a multiplication. One sort of multiplication will not be equal to B cross A. All right? We'll come to that. But anyway, so, yep.
So the last map you had on the last slide, you could do it in any order, you did the same.
Exactly, very good.
Oh,
Yep. So you could have drawn A, you could have drawn E there, and then so on and so on. Okay? All right. So A plus B, here is A. Here's A, and there is B. A plus B is C. This is B plus A. There is B plus A, and you get the same result. Okay? The next thing we're going to verify is, 4 plus 5 plus 3 equal to 4. What you could do is you could add 4 plus 5 first and then add 3 to it, or you could add 5 and 3 first and then add 4 to it. You'd get the same result. Okay, and this is called the associative law under addition, and we want to see if that's true for vectors. Okay. All we're doing is learning how to add and subtract vectors and testing out various properties. Very simple. Okay. Yeah, it does that. I don't know why. Has it caught up? What's that?
It looks like it's playing the recording.
Okay. Why does it do that? Why should it jump from live to recording, right? It does that. What's that? AI is taking over, huh? Yeah. All right, so it's caught up? Oh, wow. That's a long time ago.
what's highlighted on the top there?
What? That's recording. Oh, that's the recording playback.
Might have just stopped the recording and was just playing it back.
Oh, I see.
Where was it?
No, the red, on my thing, the red dot is,
Wait, what?
all right, so hope. Yeah, so I like to talk to the networking guys. All right, so here, what we want to see is, okay, what we're going to do is add B plus C first, and then add the sum to A. And we want to see if that's equal to if you add A plus B first and then add that to C. Okay? And hopefully the results will be the same. Okay? So here is A, B. So this is A, B, A plus B, and then here's C. A plus B and C, that's this guy. That gives you this result, A plus B plus C. Okay, so the right-hand side is you added these two guys first, and then you added this, and you got this result. The left-hand side is you add B plus C first. Okay, there is B and C. That's this guy. And then you add A to it, which gives you that, which is the same thing. You know? But we want to learn how to algebraically do that. Okay? This method is good for understanding stuff intuitively, but it's not good for doing calculations. Yeah. All right, so we'll learn things to do calculations. So here's a scalar multiplication. Here's a vector, and you're multiplying a scalar to a vector. Okay, so this is it looks simple, but well, actually, so what you're doing is this is a different beast and that's a different beast. Those are two different kinds of animals, mathematical objects. But the definition, intuitively how to multiply them. 2 times A is, a vector twice the length. So you're multiplying a scalar to that. Okay? So 3 times A is a vector 3 times as long. All right, so now we'll introduce 3 special friends. Okay. They're unit vectors. What do you think that means? Okay, what does unit mean? One? I'm sorry? Yeah, so unit is the smallest unit, which is 1. Okay, so here are vectors whose length is 1. Okay, and you'll see in a second why we'll talk about that. How many unit vectors are there? I'm sorry? I'm sorry?
Oh, 1 per dimension?
Okay, in 3 dimensions, how many unit vectors are there? 3? Okay, so here's 3-dimensional space. Let's say this is a unit vector. It can point in any direction. There's infinitely many unit vectors. In 1 dimension, there's 1. Okay? In 3 dimensions, there's infinitely many. But we'll talk about 3 special ones. Okay? So here's a coordinate system. In this coordinate system, here's the x, y, z coordinate system. A unit vector pointing in the x direction is called I. Okay? A unit vector pointing in the y direction is called j. And a unit vector in the z direction is called k. So in this coordinate system, we'll define these 3 special unit vectors. Okay? All right. So I, j, k are unit vectors, special unit vectors. Okay. Yeah. What is this guy?
5 unit vectors in the x direction.
So is it a vector or a scalar? It's a vector. Very good. Okay. This is the scalar multiplying that. Okay. So this is a vector. Okay. So let me do in 2 dimensions. So x, y. So here is I, and here is 5i. Yeah. What is this guy? I'm sorry? Vector. And it's J is, this guy is J. So 6J is vector in that direction, 6 units long. And what does this mean? I'm adding this vector to that vector. You know how to add vectors. Let's do that. So here is 5I, and here is 6J. The sum of these two guys is that. So here is a vector A, and this is a useful way of writing vectors. You'll see why in a second. Okay. All right, this is the component form of writing a vector. This guy is called the x component of the vector. This guy is the y component of the vector.
The scalars are called components?
Yep. All right. Why is that? Okay, so let's say now that we have that notation, so let's say 5I plus 6J, and let's say B is 3I plus 4J. Let's add these vectors now. A plus B equal to 5I plus 6J plus 3I plus 4J. Yep.
Isn't it associated?
Yeah.
Oh, so, okay.
8I plus 10J.
Yeah, exactly. So you just add like components, 8I plus 10J. All right. So now you have an algebraic way of adding vectors. Okay. In fact, without even realizing it, so again, A is 5I plus 6J, B is 3I plus 4. So you probably already know this, 2A plus 3B. Can you do that for me? So 2 times 5I plus 6J plus 3 times 3I plus 4J. That is 10I plus 12J plus 9I plus 12J. So you guys understand now, suddenly algebra became so easy. Okay? So once you write vectors in component forms, you can do addition, subtraction very easily. Okay? All right. All right, so IJK, so here the right-handed coordinate system. So these unit vectors are very special, okay? So again, here's the vector written in component forms. This is the x component, that's the y component. Those are the unit vectors, okay? Now, it turns out, so in 2 dimensions, how many numbers do you need to specify the vector? 2 numbers. Magnitude and direction. You can specify the vector. So the 2 numbers can be, so in 2 dimensions, to specify a vector, you can either give their components, these 2 numbers, or these 2 numbers. What are these 2 numbers? Magnitude and direction, or these are the components. Which is a better way of giving you the vectors? Which has more information in it? Which has more information in it? They have equal information in them. You can give any 2 numbers. In fact, you could give any combination of 2 numbers. Okay? You could give these 2 numbers, or you could give these 2 numbers, any combination. Okay? They all have the same content in them. But the polite way to do is either give these 2 numbers or these 2 numbers. Okay? If you want to mess up somebody, then you can give them these numbers and so on. Okay? All right. All right, so now, let's say if somebody gives you these 2 numbers, you want to be able to convert to those 2 numbers, Or if they give you these two numbers, you want to be able to convert to these two numbers. Sometimes these are useful, sometimes these are useful. Okay? So you want to be able to convert between these two guys. Okay? So if somebody gave you these two numbers, here's how you calculate these two numbers. Given these two numbers to calculate these, AX is A cosine theta. Theta is the angle of the vector. Okay? Now in these formulas, this theta is measured from the x-axis counterclockwise. So that's the rule. If the angle is measured clockwise, that would be a negative angle. Okay? So you always measure from the x-axis, you go counterclockwise. So given the magnitude and direction, here's how you calculate the components. Okay. Given the components, here's how you calculate the magnitude, and here's how you calculate the direction. Okay, so given the components to calculate that, okay. So again, what these formulas are about are AX, AY. You can go in either direction, A theta. All right, so you can calculate from components, you can calculate magnitude and direction, that's these guys. Or from magnitude and direction, you can calculate the components, that's these guys. Okay. Yep.
To calculate theta,
Mm-hmm.
it's tangent inverse times a. What is that? Is that an x or a y?
AY over AX. Yeah.
Thank you.
Yep. So these are two-dimensional vectors, AX, I plus AY, J. Okay, if these are the components. If both components are positive, then the vector is in the first quadrant. If the x component is negative and the y component is positive, the vector is in the second quadrant. If AX and AY are both negative, the vector is in the third quadrant. Yeah. If AX is positive and AY is negative, the vector is in the fourth quadrant. Yeah. You learned how to add vectors. I guess so. If you have two vectors, when you're adding vectors, you just add the corresponding components. Okay, A plus B is the resultant is AX plus BXI, AY plus BYJ. Okay. And of course, this can be easily extended to any number of vectors. So I'll make this a little complicated. 2b minus 3c would be, and let's say now there are three-dimensional vectors. So this would be AX plus 2BX Okay, help me out with the last one. Okay, so very simple. Okay, this is the way to do it. All right, so now we have learned how to add and subtract vectors. Okay, why did we do this? Well, you know, laws of physics or statements in physics are given as mathematical equations. And so here's a statement. Okay. And of course, if you have a vector on the left-hand side, you can't have a scalar on the right-hand side, or you can't have a matrix on the right-hand side. Apples to apples. Okay. So here's a vector. What this is telling you is R denotes the position vector. The subscript F tells you it's the final position. So anyway, we won't worry about all of that. This is a vector. Right now, what we want to make sure is everything else here on the right-hand side is a vector. This is a vector. This is a vector times a scalar. That's a vector. This is a vector, a scalar times a scalar. That's a vector. Vector plus vector plus vector is a vector. Okay? So apples on the left-hand side and apples on the right-hand side. Yep.
So it doesn't matter how many scalars follow the vector as long as the vector is multiplied by the scalar vector?
Yeah. And then then you have to, what other thing did you learn? You have to make sure that dimensionally they're correct. So this vector has a dimension of length. This is length. This is velocity, which is length over time times time, that's length. This is acceleration, length over time squared times time squared. Okay. So what this equation you'll see in a second in the next chapter is, this is the final position is equal to the initial position plus the initial velocity times time plus 1/2 times acceleration times time squared. What this is giving you is the position of an object, the final position of an object as a function of time. That's what it's giving you. Okay. So anyway, so mathematically, an equation or this mathematical statement should be consistent. If you have a vector on the left-hand side, you should have vectors on the right-hand side. Here's another equation. This is what Einstein is famous for. See, you're talking about him 100 years later for this little thing. This is a 4x4 matrix. Okay. You guys remember the distance formula? Okay. The distance between 2 points, x1, y1, z1. The distance between these 2 points is delta x square plus delta y square plus delta z square. Okay. I'm sorry? This is distance squared. And distance squared. All right. Anyway, so this in a curved space-time, so that was the formula for calculating distances in flat space. So if you lived on a surface like this, and you wanted to calculate the distance between this point and this point, that formula has to be generalized. This formula gets generalized. Okay? So I'll write down the formula. Okay? So, and then in space-time, G mu nu, so that's called the metric. Don't worry about it. X mu, X mu. So you see, everything is a square. There is a square, and you have to multiply this factor. Okay, so in curved space-time, that's how you calculate the distance. Okay. So again, this formula is the distance between two close-by points. How do you calculate the distance between these guys, these two faraway points? I'm sorry? You've learned calculus. To calculate distance between two far-off points, what do? You calculate the distance between two nearby points. All you really need to do is know how to calculate distance between two close-by points, and then you keep doing that, and then add them up. Okay? Anyway, that's how you calculate distances. Don't worry about all of that. So what I'm trying to say is the following. Okay, so that allows you to calculate distances. And again, this is a 4x4 matrix. This is a 4x4 matrix, and that's a 4x4 matrix. So The first thing you got to check in an equation is if you have apples on the left-hand side, what do you need on the right-hand side? Apples. Okay, that's it. Okay. Anyway, this side tells you how space-time is curved, and this is how matter and energy is distributed. So what Einstein tells you is how matter and energy tell space-times to curve. All right, so what Mr. Einstein tells you is, you might have seen this, if there's nothing in the universe, space-time is flat. You go to a store and buy a sun, the space-time curves. And then other pieces of matter go around the space-time like that, okay? So you can see that this matter told that space-time how to curve. Okay, so that's the matter distribution on the right-hand side, and on the left-hand side is how the space-time curve. So that's what that equation. Anyway, don't worry about that. All right, now we'll learn how to multiply vectors. Okay, you've learned how to add vectors. You learned how to multiply vectors. Okay, first thing is, okay, you know how to multiply numbers, right? 4 times 5, 20. Is there any other way to multiply in these numbers? I'm sorry? Oh, well, yeah. But is there any other way to multiply and get a different result? No. There's only one way to multiply scalars. It turns out that you can multiply vectors two different ways. Okay? One is a scalar product, and as the name suggests, the answer is a scalar. Okay, so you're multiplying two vectors, and the answer is a scalar. So you're taking two complicated objects and multiplying them and getting a simpler object. And then there's a vector product. You're multiplying two vectors, and the result is a vector. Okay? So we define two different products. All right, so we'll go fairly quickly. So this has two names. It's called a scalar product or also a dot product because of the notation. So here's a vector and here's a vector. And when you do a scalar product, here's the definition. Okay, A dot B, that's where the name comes. The dot product is, this is the magnitude of A, the magnitude of B times the cosine of the angle between them. Okay, so you draw the two vectors from the same point, and there's the angle between them. And so the dot product is the magnitude of this times the magnitude of that times the cosine of the angle. Okay. So here's the dot product written in terms of magnitude of the two vectors and the angle between them. You can write the dot product in terms of components as well. Okay, it's x component times x component plus b. Okay. So you see this is a scalar. This is a scalar plus a scalar plus a scalar. And this is a scalar, and that's a scalar. So that's a scalar. All right, so here's the dot product, and the answer is a scalar. Okay. And this comes about, so when you calculate the work done by a force, the force dotted with the displacement vector. Okay. And if you calculate power, the rate at which you're doing work, it's also force times the dotted with velocity. So this dot product comes up in many situations. Okay. So that's the first product. Here's the second product. The result is a vector. Okay. So C it's also called a cross product because of the notation. C, this is the result, that's a vector, and that's A cross B. Okay. And here is the definition of A cross B. Again, it looks messy, but here is A cross B. How many guys have done determinants? Okay, don't worry about it if you haven't done it. I, J, K, AX, AY, AZ, BX, BY, BZ. So the cross product is like so. It's A cross B is AY, BZ minus BY, AZ. The X component is that. The Y component is this. The Z component is that. Okay. Now it turns out that, see, 4 times 5 is equal to 5 times 4. But this cross product is not commutative. See, A cross B is minus B cross A. So the cross product is not like your ordinary scalar multiplication. You know? All right, so here's how you remember this. Okay. Again, you'll use it enough times, you'll remember it, or at least, I guess, yeah, if you become an engineer, you'll remember it. If not, you can always look it up. So here's how you remember it. A cross B. Draw a circle I, J, K, like this. Okay, so I want to write the X component. So what you want to remember is the X component of the product will not have X component of the AX and BY. Okay, A and B. So the X component is AY, BZ, AY, BZ, and then negative of the flipped, AZ, BY. So all you have to remember is that circle, okay? Plus the Y-th component. Y-th component is AZ, BX, and very good, minus AX, BZ. All right. The Z component, okay, I have trouble with this one. Who wants to help me? AX, BY.
minus AYDX.
Okay, there you go. So that's the cross product. And so you just have to remember the cross product is different. So A cross B is B cross A. Okay, and this thing comes when we'll calculate torques. Torques will be R cross F. Okay, you'll also calculate something called angular momentum, which will be R cross P. P is linear momentum. Okay, so you will do cross products several times. In the second semester physics, when you calculate the force on a charged particle, Q is the charge of the particle, V is the velocity of the particle, and B is the magnetic field. It's V cross B. Okay, so you'll come across cross products in several instances. Okay. All right, so A cross B is minus B cross A. So here's the thing. The magnitude, so see, the result is a vector. And the magnitude of this vector is magnitude of A, magnitude of B, times sine of the angle between them. Okay, so let me ask you this. Here is A, and here is B. They're parallel to each other. What do you think is the cross product of A and B?
0.
Very good. How did he figure it out? Sine of 0 is 0. Here's A. Here's B. What is the cross product? 0. So cross product of parallel and anti-parallel vectors are 0. Okay. You have to remember this. Unit vectors are very good friends. I cross j is k, j cross k is I. Again, that circle is a useful one to remember. And k cross I is j. Okay? And of course, the opposite, j cross I is minus k, and so on. Okay? So I cross j is k, j cross k is I, k cross I is j. Okay?
Is that the cross product of two vectors is always like perpendicular then?
Very good. Okay, so here's another thing. Okay, so I cross j is k. Okay, so what our friend just noticed is the following. If you have two vectors, a and b, the cross product of ab, here's how you figure it out. Okay, you turn a screw from a to b, from the first vector to the second vector. Which way would the vector move? Which way would the screw move? Okay, that is the direction of the cross product. Okay? So you use your right hand, this is known as the right hand rule. You turn from the first vector to the second vector, and the cross product is perpendicular to the plane containing the two vectors. Very good. Okay? There will be times when you won't be able to turn your hands. So, no, seriously. So this is the best way to remember it. Okay? The first vector crossed with the second vector. That's the direction of the cross product. First vector crossed with the second vector, that's the direction of the vector. First vector crossed with the second vector, that's the direction of the cross product. Okay? The cross product is perpendicular to the plane containing the two vectors. Okay, so now this is easy to remember. If you have parallel vectors, how do you define the perpendicular plane? You can't. That's why it's 0. Anti-parallel vectors, you can't. This is not defining a plane. You can't define a perpendicular. All right? Mathematics makes sense. All right.